Lần này ơi lần này non bay
quên của mở vở lại nói nhỉ công an quyết định
mời có viola để đấy.
Then I can put that in as a threshold and say I want an answer that doesn't give me more than 60% degree of saturation on this arm. And what Transyt will then do, using its optimization process, is we'll find a solution, a set of timings that try to adhere to that threshold. So the other things we can see on the screen are we can see the Q item on the top here. That's a traffic signal controller. In there, select that. We can see that we've got a timings diagram which allows us to see phases and stages. We've also got another option for viewing that same information, the stages button on the left-hand side here. So I click that one. That gives me basically the same information, but in a more traditional stage structure type format. At the moment, we've got quite a simple stage and phase structure. Using two phases, A and B, and then just running them in two different stages. Now that's because it's a default file. We can start adding in additional phases and stages in just a moment. Close those down. The next thing you'll notice on the screen is this yellow item on the bottom here, the yellow square, which if you click on it, denotes that it's also linked to the yellow pentagons as well. This is one of the ways, or the key way, when you're building a network in this form, of adding traffic flow to it. It's not the only way of adding traffic flow, but it is by far the easiest. What this is an origin-destination matrix. So that allows you to have a set of flows that say that a particular origin, a particular location on your network is the origin, and a particular location is the destination, and then a particular number of traffic flow goes between the two. So if I double-click on that, that diagram up the way, so we can still see it. What we can see then is we've got an origin destination matrix for this network, or for this junction, I should say, comprising 4 locations, 1 to 4, and then 4 locations as the exits as well. So that allows us to enter any traffic flow we like. At the moment, level 50. So it's basically saying there's 50 ECUs per hour found in between location 1 and location 2. As soon as you highlight or click on any of these, it highlights that route on the network for you. This matrix can be completed either manually, or if you've got a much larger matrix, as you can appreciate when the network is bigger, the matrix can often get bigger as well. You can also copy and paste using the copy and paste functions on the top menu here. So if you've got your OD flow in Excel, for instance, you can then just copy and paste it directly into Transyt. So that explains just about everything that we can see currently. So maybe the best thing I'll do now is I talk through some of the different modelling aspects we've got to Transyt. If I double click on the end of one of the traffic streams, it automatically brings up the traffic stream data editor item. And what this allows you to do is it kind of works as a flow process, including all the details and all the parameters that you'd want to specify for that particular. Sorry, I was getting rid of my phone call. So yeah, that gives you any parameters that you might want to change for that traffic stream, including the link length or the traffic stream length, the phase that's running it, whether it's a giveaway or whether it's priority control, whether it's signal control. Also things like flow, conflicts that it has, whether it's got normal traffic or termed normal traffic, bus traffic, tram traffic on it, and also any results as well. So everything you need relating to particular traffic streams can be found in this menu. It also lists all the traffic streams down the left-hand side, and that allows you to then cycle through those and set up the same information, or corresponding information for each of the traffic streams. So if I now move on to signals timings, if I open up the signals menu on the left-hand side here, this works in very much a similar way. what this does is it picks up every piece of information for the controller stream item rather than for the traffic streams. So what it will do is list down all your controller streams down the side here, which in this case we've only got one, we've got a simple network, and then it will set up all the phase information, all the stage information, phase delays, stage sequences, and resulting stages. So what I'll do is, because we've got a simple junction here at the moment with default values, I'll run through now with how you'd set that up. So if I quickly make a couple of changes to this network to make it more straightforward. Put that back to the right turn on it. So at the moment we've got two phases, A and B. Generally speaking, on a crossroads, that's not going to work. Or mutual opposition. So the chances are you're going to want to separate that out into maybe 3, maybe 4 phases. Something that works probably differently. So let's show how you do that. So if I was to do that, I'd want to add some more phases in. At the moment we've got A and B, those are the ones that are set to put in there as default. So to add more, you just simply click the Create New Phases option on there. I want 4. Click OK. It asks me whether I want to add 4 additional ones, or whether I want to add those 4. Whether I want 4 new ones, scrap the old, or whether I want to add to it. I'm going to say yes. Let's remove the others because I don't want 6. And we end up with 4, A, B, C, and D. Incidentally, if you're overseas and you don't use A for phases or terming phases here, then you can change that to letters as well, or numbers as well. So you've got free reign of that. That allows you to also set the minimum green time, which is typically 7, so that's what we've used as default. But again, you can change that to suit your local scenario. So now we have the phases that we need. The next step we need to work through is setting up the conflicts between those phases. So to do that, we click on the intergreen matrix on the right-hand side here, and we see that we don't have a conflict between them all. Now I'm going to run these all independently in their own stage to keep it nice and simple. So for that, I'm going to need an intergreen between every single one. And as you see, as I start filling in the intergreen matrix, it will start adding zeros in the other side. What that's showing me is that if the conflict goes one direction, it's also going back the other way. So we do need to make sure we've got suitable intergreen times in there. Now I've got a nice complete intergreen matrix. We can see that no 2 phases are going to be able to run in the same stage, so it's going to require 4 stages to run this. Incidentally, I'll just mention the other 2 tabs on here. You can see we've got an interstage matrix, which, because at the moment we've got 2 stages, it's giving us the length of the longest intergreen between those 2, which is 7 seconds. And we've also got the option to ban stage changes as well. So as we start making more stages, we'll then put more boxes on there. So if, for instance, I didn't want to go from stage 4 back to stage 1, I can put a tick in that box, and it will stop that being one of the stage sequences. So it just gives you a bit more control. So now I've got 4 phases, I've got some intergreens set up, so I know what conflicts with other phases. If I just go to the stage library there, it's just a case of auto-generating stages now. It gives me a quick warning to say that it's going to get rid of what's there currently, which I'm happy with, and it's now auto-generated each of the stages, so it knows, because of the intergreens that I've entered, that A, B, C, and D must run in individual stages. I won't do anything with phase delays at the moment. I'll show you how we can manipulate those afterwards, once we've got a sequence. So let's move on to doing the sequence. At the moment, we've still got the default one in there, which says we've got stages 1 and 2, which obviously we know now that we're going to need more than that. So it's just a case of clicking auto-generate sequences. Again, it gives you a warning to say what it's going to do. What it does, it will generate the 10 shortest sequences. In this case, I shouldn't have thought there was going to be 10, but as it gets more complex, there will be. So that will look for the most efficient way of running those stages in order. And as we can see there, we've got a sequence set up. The first one on the top there is running at stage 1, then 3, then 2, then 4. And that's the sequence that we're using, shown by the box at the top here. If I want to use a different sequence in this list, either 2, 3, 4, 5, or 6, then all I need to do is just change that number at the top there, and it will allow me to change which sequence I'm using. I'm going to stick with 1 for now. What we can see from that is we've now got a link to the two ways of looking at that sequence. So we've got a timings diagram that now shows we've got phase A, B, C, and D, and when those are each running, which are in stages. So A runs in stage 1, B runs in 2, C runs in 3, D runs in 4. And it also shows us the intergrade between. The other option on there, again, shows us that in a more traditionally diagrammatical form, you'll see in the controller specification document. So what I need to do now, as you'll notice on that diagram, is that some of the phases are not coloured on here correctly. And the reason for that is because this takes its information from the network diagram. And as we'll see on the network diagram, we've set up signal timings with phase A, B, C, and D. What we haven't done is told the Transyt program which part of the network is A, which part is B, which part is C, which part is D. So it doesn't know that yet. So that's why that stages diagram doesn't look good. So as we can see, we've got A and B in just the 2 side codes there. I know we need more 4 stages, so I'm going to change this one to C. So we do that by double clicking on it and changing the phase to C. And I'm going to change this one to D. So now if we look at it, we've got phase A, B, C, and D. And I think if I now look at the stage diagram, we can clearly see that that's now updated. The fact that we've got A, B, C, and D, so we don't have any that are all where we did before. I mentioned I'll also go back to talking about phase delays. The way we can do that is there's 2 ways of entering phase delays. Some people are more happy with entering phase delays in a text-based form, that they're allowed to, they'd like to specify a phase delay saying, I want to delay phase A, or change from phase A to B by however many seconds, do that in numeric form. Others prefer it on a diagram. So if I open up the phase delays box now, you can see we haven't got a phase delay there yet. Open up the timings diagram at the same time. See, there's 2 ways of doing this. So you can either create new delays by selecting the box on here and go through it in a text-based form, or you can drag and drop on this diagram here. So we can quickly slide a losing delay there, and we'll see that gets added in to the phase delays box automatically. Same with the gaining delay if you so wish. So that's a quick way of doing it. Again, if you've got this data that you want to copy and paste from elsewhere, then in text form you can do, but also you've got a diagram to help you with that too. So I shall remove all delays just to keep it nice and simple. So now once we've got our signals timing set up, and we know about flow now, I haven't changed the flows, but we can run with the default flow we've got there. The next step is to run the file to find out what kind of answers we're getting. So to do that, we've got the Run Transyt button at the top here. And we can't do that because we've got errors in the task menu. That's actually a good reminder for me to remember to tell everyone about the task list. What this task list does is it shows us that if there's any inconsistencies in the network, that you then have to change those before it's going to be able to run. Just see if I can fix this one quickly. Go through the whole file to find out what I've done wrong to get that error there. But the running the transit is through that top button at the top there. So what I'll do is I'll just, for demonstration purposes, I'll open up the file at the top just so that we can run it. So this one's the same, except I haven't messed this one up. So when you run transit, it takes a few moments. In its simplest form, it's quite quick. And when it gets slightly more complex networks and start using some of the more complex models, it gets more slow to run. But generally speaking, we're talking a few minutes here to get an answer out. In this case, we've got an answer very quickly, and what it does is giving us a performance index. The performance index value is calculated using stops and delay values for the whole network. So that's how Transyt finds its best timing solution. So what it does is it works out a set of timings and then calculates how many stops and delays there are on the network by using those timings. It puts a numerical or financial penalty against each of those stops and each of those units of delay. And for every set of timings, it will then come up with this performance index value. What the Transyt optimizer does is it hunts for the best performance index. So it finds the solution that gives us the least stops, the least delays on the network. In this case, it's turned out that there still does need to be some stops and delays on the network, as is often the case, and that's been attributed to roughly £46.26. Those values are taken from the department. And they can be totally manipulated by the user as well. We've just put those in there as a default and a suggested route for stops and delays. If you've got more accurate or more specific local research, you can change the values that the optimizer uses. Likewise, you can change the units it's in as well, so you don't have to worry with penalties. The other results it gives me are the average speed on the network, so a slow average speed on there, and start seeing where you've got particular bottlenecks or problems with a speed of roughly 17 kilometers per hour on a single junction like this. I would suggest it's relatively traffic free and probably okay. If we're starting to see average speeds much lower, then we've got some issue somewhere. There's obviously some sort of queuing. We've got the overall network delay as well in piece units per hour. And we've also got the highest degree of saturation, the highest being 19%. So at the moment we're showing that this junction is fairly happy. And don't forget this was actually running in the just 2 phases as well, 2 stages. This is the default version. So overall, the Transyt program is telling us that those timings or this situation is in capacity. So the 2 options you're presented with at the bottom there are kind of what you really want to get out of Transyt. It's the whole purpose of doing this modelling is to get some signal timings out. So we can either do that as either periods or stages. Basically, they take you to the same sort of place. They take you to these 2 screens here, independently. So what this gives us is, because we use the 2-stage default version, it gives us the start times and the end times of those 2 stages, stage duration, and the split. So these types of timings can be taken forward to a controller specification or appropriate to mutate a UTC system. And you've also got your green periods there as well. So that's the answer you want to get out. That's it in its quickest form. We do also have this button at the top here, which we won't run through everything today because it's a long report, but it will give you a full report of all the input data against all the output data, and give you a breakdown of every piece of analysis you could want. Generally speaking, this turns out in a multiple-page document, and you can pick and choose bits out of that to use in your submissions to local authorities, for instance, to demonstrate how your transit models actually work. So that's a full report, if you like. These ones on here I'll give you links to the critical information, the thing you're actually interested in straight away, and then you can fill in the more detailed parts later on, should you need them. So I think remaining time, I'm just going to talk about a couple of different traffic models in Transyt, and maybe just a couple of different optimization procedures. Now we've seen how Transyt works on a single junction. As you can appreciate, on a single junction, it's quite a simple task for it to achieve. But as you start building up a network, it starts becoming a bit more confusing and a bit more of a challenge for this optimizer to work. So I shall open up a junction that actually has some progression in it. I'll choose that one. What this one shows is a 4-arm signal control roundabout. So what we have on here, as we'll see from the diagram, whereas the other junctions will have 1 signal controller and quite a simple setup, this one's got 4. So not only do we need to work out the split between the entry arm and the circulating carriageway for controller say 3, we also need to work out how that's offset against 4, 1 and 2 to make sure we keep the circulating carriageway in the centre of the junction nice and free. So this is now going to challenge the optimizer a little bit more, but it's something that this is what Transyt is based on, this is what Transyt is designed for. So the kind of things we're interested in looking at, we've got 3 different traffic models in Transyt. We've got the traditional platoon dispersion model, which any users of earlier versions of Transyt will understand and be happy with. We've also got the CTM model, which stands for the cell transmission model. What that does is it doesn't model the dispersion of a traffic platoon from one stop line to the next. It models closely spaced stop lines. So specifically, CTM has a real application at a signal controlled roundabout like this for your circulating carriageway. What we don't want is queue to queue back from this stop line all the way through to the previous stop line. So by modelling it in the cell transmission model, what that allows us to do is it allows us to model the blocking back effects of traffic from one stop line to the next and try and alleviate those problems within the Transyt optimization process too. The platoon dispersion model, the traditional one, is more suitable where you've got stop lines that are further apart, and as you want to model traffic leaving one stop line and then arriving at the next stop line, you want to get that offset timing spot on. That doesn't happen on closely spaced stop lines to a great degree anyway, so that's why the CTM model has taken that aspect of it out and focused on the blocking back. The platoon dispersion model takes into account the fact that as traffic progresses from one stop line to the next, some traffic pulls away faster, and some traffic might pull away slower, some turns off, some joins in. So the shape of the platoon further downstream at the second stop line is distinctly different from how it left the first stop line. Now getting that platoon shape, the downstream stop line accurate, is the key to getting the offsets between 2 stop lines and 2 junctions correct. So that's why we've got those 2 models. The third model is called the CPDM model, which stands for Congested Platoon Dispersion Model. This is designed for flared situations up to sort of 30-ish meters long, where you've got a flared situation at a stop line. That's basically what it's been built for. So to set these particular traffic models, we can do that on either a network-wide basis, or, which is more likely that we're going to want to do, on a traffic stream by traffic stream basis. For instance, if I had 2 roundabouts here and I had a second one over this side, I would want to get the platoon dispersion effect between the 2 roundabouts correct. Likewise, I'd want to get the blocking back effects on the roundabout modeled accurately to make sure I didn't cause myself problems further upstream on the circulating carriageway, or worse still, block the entire roundabout. So I will want to use these models on a link-by-link basis, or traffic stream by traffic stream basis. So to do that, that was one of the options that we find in the traffic stream data editor. So we have on here, traffic model here. It gives us the option of either network default or the 3 that I've just run through, the platoon dispersion, cell transmission, or the congested platoon dispersion model. At the moment it's on network default, so we have an option to either set this via a whole network or via individual traffic streams. So I can now select this to be CTM, and likewise I probably want to set these others CTM as well. So I can cycle through that by looking for AC1, that one there, this traffic stream here. Sorry, I moved things around too many times. As you can see, as I click on things on this list, it highlights orange in the network diagram. So I'd also want to set that one as CTM2, and likewise I'd want to do BC1. And I'll also do CC. So it's as simple as that to change the traffic model between the 2. So closely spaced stop lines, we're using things with the model CTM to model blocking back effect, and for much longer lengths of traffic stream, you'd be looking at using the platoon dispersion model to model the dispersion effect from one stop line to the next. So as we start getting more complex networks, these models start making a much bigger difference to the network architecture. The next thing I'll talk through is the optimization procedure. as we saw with the first junction I did, we had a very simple junction, and the optimization procedure was very, very quick. That's brilliant for that simple junction. That used the standard hill climb procedure that we've used in previous versions of Transyt. However, hill climb is a very good model for giving a very good answer in a very quick amount of time, because it's a very efficient way of finding the optimum result. What it doesn't guarantee you is it doesn't guarantee you that it finds the absolute optimal result. So there may well be a better one out there. What we've done to combat that is, if you look at the main menu on the left-hand side here, we've got optimization type. We've basically built in 3 different optimization types: fast, medium, and slow. They always use slightly different mathematical procedures to them, so the actual optimization process is different. And based on that, it can take longer for the slower one than it does for the fast one. But what the slower one will do is it's a far more detailed mathematical procedure, and it's likely to return you a slightly better result. So for simple junctions and for small networks, stick with the fast option, because it's going to give you the best result in a quick amount of time. If you're building a more complex network, something that you feel maybe there's a better result out there, then maybe experimenting with one of the medium or the slow option, they could then return you a slightly better result. So you've got the flexibility to either have a quick result and get a good quick result, or whether you want to get a more detailed result and potentially a slightly better result if you've got the time to spend on it, or if the model dictates that it's necessary. So I think that was all I was going to talk about today. Hopefully that's given you an overview of the Transyt front end and the sort of functionality of it. As I mentioned at the beginning, we don't have endless amount of time in a webinar to go through every piece of information. Is there anything anyone would like to know specifically? I have noticed on the left-hand side I've had a couple of questions in. Just try and get hold of those. I will see if I can address those. Okay, I've had one member, one delegate asking, can we explain the integrine matrix again? Yes, that's no problem at all. So let's use this as the example. This is quite a simple example, actually, using this roundabout. Actually, no, I won't. I'll go back to the earlier file. It's actually a bit more complex in there. So if we can see now that we've got the original default crossroads back on the screen, we'll note that we've got 2 phases here. So traffic from this arm A, is going to turn right, left, or ahead. It can only do that if it's not got conflicting traffic coming out of this side road, or this side road, or this arm here. So we add integreens in to make sure that traffic movements that we want to run independently are sort of logged, if you like, as having a conflict with another movement. So you can run 2 movements that have a conflicting space together, and they won't need an integrine, but they will have to work using the opposed right turn model. If you want to keep them totally separate and make sure that they run in different phases, then the only way of doing that is to enter in an integrine between the 2. So if I open up the integrine matrix on here, we'll see that we've got between A and B, there's 7 seconds. So what that says is, after the last vehicle crosses the stop line on A, it requires 7 seconds to clear the conflict point before traffic on B will be released. There are a number of different ways of measuring integreens and setting integreens throughout the world. In the UK, we use what's termed the X distance, which is the distance, the conflict points from both stop lines. You subtract one from the other to get the value, and that value is then used on a lookup table to count it to a certain number of seconds of integrine. So that's a standard procedure that the UK traffic engineers will use. I appreciate in the other parts of the world they use road speed, all sorts, and there's an equation that they put all that information through, and that will come out with a number of seconds that are required. So there's a number of different procedures. Transit doesn't really mind about how you're working out these intergreens. All it wants to know is what that number is, what is the clearance time between one phase and the next. I'll also point out, while we're talking about phases and things, something I probably should have mentioned earlier on. In the UK, we term traffic phases as being a particular movement of traffic. We term as traffic stage as being a collection of phases that run together in one period of time. I appreciate, again, in the other parts of the world, we have different terminology for that. Certainly in the case of Australia, they use phase and signal group. They use phase, where we would use stage, to denote a selection of movements running together, and they use signal group, where we would use phase. So that can become a little bit confusing when you're starting to use a product that's using the wrong terminology, and even when there's an overlap of one word, then it starts becoming a problem. What we've done is we built into Transyt in the file and then preferences option. We have built in there a terminology change option, which there we are, it's on there. Under localization, we've got phase, stage, display names. We've got it set to phase being phase and stage being stage, but there's also an option to be signal group, stage to phase, and then phase to signal group as well. So there's a number of different options we can have in there to change all the terminology throughout the product. Hopefully, that should give you the right terminology that you use in your local country. If it doesn't, then do get in contact with us and we can always make another change. We only added this in because customers have asked for it. We've been reactive to the customers who've asked for it. We haven't necessarily guaranteed that everybody, the terminology that everyone uses is catered for here. If it's not, let us know, we'll do something about that. The second question I just had in is there a network size limitation, a number of controllers, nodes and links? There is, the number of which escapes me now. It's so big that you probably won't need to worry about that. For the case that I think the limitation we've only put in there is because of processor power. If you start getting more than, I think it's something like 50 or 60 controller streams, if you start getting more than that, then the processing power of most computers is struggling with the Transyt equations anyway. So the limit we put in, I guess, is arbitrary, really. You can move that if you feel that it's necessary. But it's also a point to remember that the limitation or the design of Transyt is that it's around a single cycle time or a multiple of that single cycle time. So we've got to think about how big a network you're actually going to be running on a single cycle time. If you're going to run it all at 50 seconds, then you're probably not going to have a massive number of controller streams or nodes. Pushing over 60 running on the same cycle time, it might be possible in certain locations, but more often I would imagine you'd split that into a number of different cycle time regions in your network, and probably want to model each of those separately. But if you do find that the limitation in Transyt is causing you a problem, you want to add some more traffic controller streams in there, then please just get in touch with us. We can always lift that limit. As I say, it's not been put in for any reason other than making sure the processor power is kept in check. Follow-up question to that is, do the results significantly differ from a comparable network using a linear analysis? Obviously, working for TRL, we don't like to go down the route of comparing products with Transyt. It's a very comparable product and one I've personally used hugely in the past in previous roles, and one that I certainly am happy with. However, the results between the two, every time I've ever done the comparison, it's been very similar. That's not to say they work in the same way, though. There are certain benefits of using Transyt, there are certain benefits of using Transyt. Certainly, I think on the benefits on using Transyt in this case would be the CTM model, being able to model the blocking back. So I think that would be the sort of the key message to get across there is that if you're modelling two scenarios or modelling the same scenario in Transyt, the ability to model the blocking back in CTM is probably going to give you the better answer if that's required of your network. But to compare the two answers is kind of an open question, really. Follow-up question here as well. How does Transyt differ from Arcady and Piccadilly? Well, Arcady and Piccadilly will be features of a totally separate webinars, but I can touch on basically on what they are for. Arcady is our priority roundabout control model. What that allows you to do is work out the capacity of roundabouts based on geometric parameters, and Piccadilly does the same with priority control. There is an element of using both software products through the Transyt front end. If you have Arcady on the machine, you can use those equations, those geometric informations through the Transyt front end to get your parameters. So they are complementary products, if you like, both made by TRL and both sort of subject to their own webinar, if you like. There's a huge amount of information to go into on those, so I won't touch on that now. But the key point to remember is yes, you can use Arcady and Piccadilly equations through the Transyt front end if you have those licensed on your machine as well. Second question here from Adrian. Which would be good for a local authority in London to specify? I presume you're relating to which either Lindsig or Transyt would be good for. Okay, all right. There's not a question. Brilliant. I'd say that yes, both products are in the market, both Lindsig and Transyt. Both do ultimately the same task. Both go about it in a slightly different manner. I think that's probably the best way of phrasing that. If there aren't any other questions, then I think we'll call that a day there. What I will do though is I'll put into the chat window there, the email address for TRL software. If you have any further questions, please do send it in to TRL software, and it can be asked by myself or by one of my colleagues. And by all means, get back to you with another answer. Obviously, there's other questions you might come up with in the next hours or so, or the next day. If you have further questions, by all means, get in touch with the software at trl.co.uk. Thank you very much for joining us today. Appreciate your time. Hopefully it's been useful for you, and look forward to speaking to you on future webinars. Thank you.
trước. Đấy. Đấy.
Tắt cái gì đây? Tuyên bố cái thật là